All right, so we're back with Graphics Interface 2020. It's now my pleasure to hand it over to Brian Weibel, who will introduce our next speaker. Brian, you can take it away.
Hi, I'm Brian Weibel. I'm the chair of the awards committee for Graphics Interface, and it's my pleasurable duty to introduce Dinesh Pai, who's a Tier 1 Canada Research Chair at UBC, and best known, I think, for his work on human research. I was going to say human animation, but it's a lot more than that. Early human animation researchers, I think, concentrated on making the visual part of the animation look as realistic as possible. But Dinesh has gone well beyond that in adding some science. He has an amazing lab full of accurate scientific instruments measuring all sorts of things, the Sensorimotor Systems Lab at UBC. So please welcome the CHCCS 2020 Computer Graphics Achievement Award winner, Dinesh Pai.
Great. Thank you very much. Let me, I think, share my screen first. Can get that. All right. So first of all, actually, thank you, Brian, and thank you for the CHCCS for this wonderful award. I'm really honored by this recognition. As you know, any award like this is really a recognition of all the creativity and the hard work of all the students, postdocs, and my collaborators, many of whom are in this audience over the years. So it means a lot to me. So I was trying to put this talk together, and I thought, since this award says I know something about computer graphics, I thought I'll try to answer a few questions from my experience that especially young researchers may have. So things like how to get started in computer graphics. This is what actually Doug asked me during his interview. How do you choose a research topic? And how to have a good career in computer graphics. So I thought about this quite a bit, and I tried to put this talk together. I think the short answer is to do the exact opposite of what I've done, because I think I've kind of approached this whole thing from a very complicated way. At least that's the short answer. I'll try to give a longer answer by giving examples from my research and try to summarize some observations at the end. So I actually, started very far from computer graphics or North America. I studied as an undergraduate in India at the IIT Madras. I was studying mechanical engineering. I was a pretty good student, but I spent a lot of time doing things like organizing cultural festivals and things of that sort. But I had the good fortune of taking a course with this guy, Professor Vijayaraghavan, who in his tests always gave one question that was supposed to be very hard to answer. And I saw a very simple, easy way to solve it. So he was impressed, and he pulled me into his lab and said, let's do some stuff together. We published a paper in thermal conductivity in heat transfer. Nothing to do with graphics. But it caught the attention of this guy, Ken Torrance at Cornell, who was a well-known figure in heat transfer, and he got me to come to Cornell to do my graduate study. At that time, when I arrived, actually, he had just recently worked with Rob Cook on the the Cook-Torrance reflection model. I had no idea of anything about that sort. So I guess this was my first near miss of working in graphics. It turned out that, Ken said, I'm not really working on heat transfer anymore. You should work with this other junior prof that we just hired. And that actually didn't work out so well. So I switched fields from heat transfer to robotics. So, and I worked with Professor Ming Lu, who had just joined Cornell from Berkeley doing robotics, and he said, you know, hey, I got this account in a facility they've just set up next door called CADIF. So Don Greenberg had just set this up, and at that time it was one of the most amazing places to do computer graphics. So by pure chance, I had ended up, you know, next door to one of the best places in the world to do computer graphics. It is actually pretty impressive. They had a wax 11780, which I think at that time could do 1 million instructions per second. It was really fast. One MIPS machine. We had an Evans and Sutherland picture system 2 that could show wireframes, and you could rotate this in real time. It was pretty awe-inspiring. So I actually took my first graphics course with Don Greenberg. And I also had my first encounter with Canadian computer graphics research by meeting John Dill, who was a CADIF manager at that time. It wasn't under the best of circumstances. It actually, John caught me using my advisor's login to work on my work, and said, "What are you doing here? You know, you're not Ming Liu." And he pulled me into his office, and he gave me a bit of a talking to. But he eventually gave me an account on this machine. So I wrote some computer graphics software, and I guess this could be my first graphics paper, though it wasn't a real graphics paper because it was published in a robotics conference. But it anticipated this idea of digital twins that is now very popular with Industry 4.0, and the idea was that you could virtually prototype a robotic work cell, write programs for it in Lisp or something like that, and then we could simulate the heck out of it, make sure that all the bugs are gone, and then when you're happy with it, you would actually make it run on the real robot. So this was a lot of fun, and I enjoyed graphics very much, but I was still very much interested in robotics. And I noticed that there were some problems with this kind of robot. The robot would do mysterious things, like every now and then it would be just moving along, and it would suddenly have some weird behavior. And I later figured out that it was because it was hitting a singularity at the wrist. And it was also that it was kind of a self-inflicted wound, because it was not necessary to have that singularity, but somehow the way we programmed the robots made it happen. So for my PhD, then I kind of did a bit of a deep dive into many things. I took advantage of Cornell's philosophy that you could study anything you want. So I did some differential geometry, try to classify robot singularities, but I also was very much interested in understanding those problems that I was seeing and how humans solve the same problems. So this has been a lifelong interest for me. Actually, I think for any roboticist, roboticists are in some kind of a human envy situation, because we always see how easily humans do the things that robots have a hard time, and we try to figure it out. So I had this naive grad student's idea of saying, I'm going to go take a course with a neuroscience prof, and then I'm going to go and implement all these solutions with my robots, and it's going to work. It turned out it wasn't so simple, but I did learn some things. For example, this is the animal that Avis studies, and so not the big fish, the little parasite on the side here, the lamprey, and it's like the most primitive vertebrate. And what's interesting about it is that you could take out its spinal cord and just put just the spinal cord in a bath and dump some neurotransmitters in it, and it fires in a pattern as if it's actually swimming. It's called fictive locomotion. So it seems like the animal is wired, the neuroscience, the nervous system is wired so that its natural dynamics almost does the right thing. And then the environment shapes it with feedback to actually do the swimming. So this was an important insight that I tried to take away in my later research. So after my PhD, I kind of immigrated to computer science from mechanical engineering. I worked with John Hopcroft's Newton project and also with Bruce Donald. Hopcroft had gotten this very large grant, and so he gave me a free rein to do pretty much anything I wanted. So I did work on trying to implement this kind of ideas with a walking machine, the walking robot. I'll try to briefly summarize this paper just because, not because it's actually one of my least cited papers. I don't think people have noticed it that much, but I think there's some interesting ideas there. So the idea that was that, suppose you want to program some movement, and I think this applies for animation too. Suppose you want to make a robot and put something on the table. The standard way is you give it a trajectory, you make up a trajectory, and you say, okay, this is how you move to put something on the table. The problem with that is that you have immediately thrown away all the degrees of freedom that it had with an artificial requirement that it has to travel in a straight line, and then this is the kind of thing that gets you into singularities. So the idea of least constraint is that you specify this motion declaratively by putting all the constraints that you really want it to satisfy. And so, for example, to say put something on a table, you'd say, hey, don't go outside these constraint areas. So anything inside this large volume is okay. And if you want to say get closer to the table, you can put a constraint like that animates, that moves down. And if you want, now this will say you can go put it anywhere on the table. So, and then you can add more constraints if you want to specify where it goes until you come up with a plan. So this is a way to utilize the natural dynamics of the system. Remember, like in the lamprey, if the arm just wants to fall in a natural way to some place, let it do it, as long as it's not violating any hard constraints. So that's the idea, and I try to implement this.
The following depicts the control of human-like walking using our least constraint approach for motion specification. The walking machine model has 3 degrees of freedom hips and revolute knees.
Can you hear the audio?
We simulate the full nonlinear rigid body dynamics of the machine. You have just seen typical examples. We can also produce diagonal and backward walking. The least constraint.
Oops. So I'm not sure if I can see the chat window here. Because Fanny can tell me if you can't hear it. So one thing about this, by the way, I just wanted to mention is that I actually submitted this paper to SIGGRAPH naively without knowing anything about how things should work. It was rejected, and actually I never published it except as a tech report, even though it did get noticed. I think I know Jessica Hodgins and other people cite the tech report from time to time. So I think it was it did have an impact. It was kind of interesting. We programmed this full dynamic locomotion with this constraint system. So at that time, then I moved back to, not back, actually visited for the first time Canada when I interviewed, and then I fell in love with UBC and Vancouver, and I moved to Canada. So the next stage, I was still continuing robotics, and this period I had nothing to do with graphics whatsoever. But I tried to use this constraint-based programming to program robots. Again, the idea is, if you want to build a locomotion system, why do you want to constrain yourself by saying the legs have to look like humans? The legs could be on any side of an object. You could build a spherically symmetric robot, for example, like this four-legged one called the Platonic Beast that I built just after coming to UBC. Actually, I'd asked Hopcroft if I could build it at Cornell, and he said no, but once I got my own faculty position, I could do whatever I wanted. So I built this thing, and so it could locomote like this. So because of its spherical symmetry, it could roll and synthesize its gait as it goes along. It was programmed just for these kind of constraints, as you said. So again, you see the idea, if you remove unnecessary constraints, then you can come up with interesting new solutions. By the way, as an aside, during that time, I had the good fortune of working with this amazingly talented engineer, Rod Barman. He was on our staff at LCI, and he came back, you'll see it later, in some of the work that we're doing. So I also worked with Alan Mackworth on his Dynamo Robot project, which, by the way, was the inspiration for the now famous RoboCup. After we've been doing these robots for a few years, we had a visit from people at Sony, and then they took it and made it into this worldwide phenomena that it became. I also worked on robotics with Matt Mason during a sabbatical on a multi-wheel robot called a manipulator. I was doing this kind of stuff. I was having a lot of fun. Got quite a bit of press. People liked the way it looked. But interestingly, a few years after we built it, CMU and NASA sent a robot mission called Dante 2 into a volcano in Alaska. And it was actually an amazing feat of engineering. It's a great robot, but it was a traditional legged robot, which had a preferred up direction. So on the way back, when it was coming back up, it had a little slip and it actually fell on its side and it couldn't get up. The robot was not damaged, but it just couldn't get up. So now you have a damaged robot in the middle of a volcano. They had to send down some grad students to try to pick it. That didn't work. They tried to lift it with a helicopter. That broke. All kinds of things like that happened. And so it made the case that, maybe for a robot, you can build, if it is spherically symmetric, there are some advantages. So coming back to graphics, just around this time, this was my gateway from robotics to graphics, which was through an area called Haptics. And in Haptics, one way of thinking about Haptics is it's a lightweight robot that interacts with your hand. I had a project with Vincent Hayward at McGill, and he had sent me this robot that you see, a haptic device that you see on the right called a pantograph. And I asked a master's student of mine, Juhani, to write a hello world program. I just take this thing, which is essentially like a 2 degree of freedom mouse, and go and touch a circle, hello world thing. And the contact algorithm had some small instability, so every time you touch it, it could vibrate. Go, eh. And every time it went and touched it, you got this amazing, compelling experience that you were touching a real object because you felt it in your hand, you heard this vibrating sound, and you saw the motion with incredibly good synchronization. It was a pretty cheesy line drawing graphics, but I think to this day it's one of the most immersive experiences that I have seen. So I realized that what we were doing with haptics is not just applying forces to the hand, but we were simulating contact, and that contact involves a sensorimotor loop. That you see some object, you take an action, but that action produces not just forces or visuals, but it produces a multisensory response. And large parts of your brain are processing this with very low latency to figure out what happens. So I was inspired by this insight to say, let's study how to synthesize things like sounds by themselves. So I had a grad student who was also a musician, Case van den Dole, and also a former physicist. So we built this system for real-time synthesis of shape-dependent sounds. And by shape-dependent, I mean for real objects, for example, like here is a little prop here is a pot. The sound it makes depends on where you're touching it. You know, you're touching at the bottom, it has one sound, and these are just due to the physics of vibration and the boundary conditions on it. And we figured we could compute that. So we computed, for example, in this little early demo, the sounds for all kinds of things. You'll even, some of you may notice an L-shaped table. The significance of this L-shaped table, which is the same as you will see an L-shaped mode on MATLAB's covers, because that was Cleve Moller's PhD work to compute the eigenfunctions of these kinds of domains. So we could compute the sounds that would be made depending on where you tap on this, and we did a lot of live demos like that. Oh, by the way, we also submitted this paper to SIGGRAPH. It got rejected. And I think the reviewers said, you know, that's kind of interesting, but what we really need is animal cries, and you can't do animal cries, so too bad. So that was again not my first real graphics paper. So this is my real first real graphics paper with Doug. So that was kind of an interesting thing. So I'll play the video here. By the way, we were so naive at that time that we didn't even get the video in time to submit it. So it was the first, I think, animation paper to probably have gotten in without a video, but it did get in. So we submitted this video afterwards. So, but actually, even though the graphics was cheesy, we had, I think, a lot of interesting ideas in it. We showed how to use boundary element methods, which would be more suited for graphics because it's all boundary-based computations. We showed how you can pre-compute reads functions, fast capacitance matrix algorithms, all that kind of stuff. But I think more critically, we showed that you could start with a full physical model with a classical numerical method and do model reduction in a principled way to make it work in real time. And it worked in real time with haptic feedback, even on like 20-year-old machines. So we could do things like, this was actually, we demoed this at SIGGRAPH, that you could touch this with a haptic vibration feedback. We could interact with a phantom device, running the control loop at 1 kilohertz. So this was very interesting. This is actually a very interesting time also in terms of hardware advances. And a couple of years later, the GeForce 3 came out. And for people who may not remember, this was the first programmable graphics consumer level piece of hardware, GPU. So we realized that this is really well suited to doing modal synthesis, that we could map all the mode shapes onto vertex attributes in the GPU, and then we could do real-time dynamic simulation of deformation on GPUs. So I think this is probably the first GPU type of method to be able to do physics on GPUs. Of course, Doug had to write this code in, I think, using assembly language or something like that at that time. But as you can see, before DIRT, you didn't have this type of secondary motion that you could apply. But once you could do that, so you could generate these types of oscillations with costs that are pretty much the same as just shading or rendering the object. Okay, so I continued on with looking at combining sound with other modalities, like such as touch. So, for example, with Derek DeFilippo, who is another musician, there's one good thing about working in sound is that you can get people with useful hobbies to be interested in this. So, so we were looking at how we could simultaneously, with very low latency, essentially zero latency, because we synchronize the forces that you would feel in your hand and the sound that is produced. So this is the audio haptic interface that we presented at WISP. Also coming back to graphics, and now I was really getting into graphics as my main research area. Paul Cry, familiar to all of you, had just finished his master's thesis in which he had done some very nice contact and sliding work with smooth surfaces, and we thought we could use that to generate dynamic animations with sound, again tightly synchronized. So as you can see, I'm assuming that you can hear the sound. I'm not seeing any complaints here. I should probably check my chat window to see if this is all good. So as you might hear there, that the sound is able to convey things that are very difficult for you to convey visually with graphics, such as when is the object rolling, when is it sliding, and those types of things. Okay, oops, let me. Okay, so so far, all the things that we were doing were based on textbook physics models. You kind of read up the equations and you would implement them. But I had this nagging feeling that the world is more complex than that, and that we were missing a lot of the complexity by just assuming that things were very simple. So if you take a stuffed toy, or here's another example. That one is in my lab at the moment. So if you take a simple thing like this, its behavior to actually build a model of the real toy would be complicated because it's not just a uniform elastic object. It's got a surface which is furry. It's stuffed with something else, and it's got some seams at various places. So when I bend this, it just hinges almost at the neck because of the seams. So if you're interested in building a model of a real object, then your big problem isn't what are the equations of motion of elasticity. Your big problem is, what is this thing actually made of? So I started this project. It was a very big multi-year project to build a measurement facility to actually capture these types of properties. And my hope was that you could send in an object, we'd put it in there, and we'd build a physics model of the object. I'm going to just play a video here from that era.
Models of physical interaction behavior are important for rendering objects in simulation and virtual environments. Such models include deformability, contact texture, and sound properties. The UBC Active Measurement Facility, or ACME, is a system we have developed for automatically acquiring such models, equipped with cameras and rangefinders, positioning devices, and a robot manipulator. The system first creates a surface mesh for the object on which the behavior models are registered. This is computed from stereo range data. A texture map is created using color images from different viewpoints. One important behavior that we can capture is the global deformability arising from local contact. This is modeled using Green's functions, which provide an efficient means for simulation. To capture deformability, the system applies known contact forces to the object. Optical flow information from range data is then used to estimate the resulting deformations, from which the Green's functions are then estimated. Another behavior is contact texture, which includes roughness and friction. To capture roughness, the robot strokes the object and examines the resulting force profile. Smoother surfaces result in smoother profiles. Friction is determined by stroking the object in opposite directions and examining the difference in tangential force. Contact sounds of an object, which typically depend on location and surface texture. The robot collects sound samples at different points on the object's surface. The resulting waveforms are analyzed in the frequency domain to create sound models based on. Contact texture information can also be used to model sounds associated with scraping.
So, so we had a lot of fun. We built this with this machine, and actually it led to both advances in sound synthesis as well as in haptics. But just around that time, I also got some itchy feet. I'd become a full professor at UBC, and I moved to Rutgers. And I very cleverly took a lot of my UBC students with me, including Kang Yen and Paul Cry, as well as convinced a couple of undergraduates from UBC, Shin, Sueda, and Tim, to follow me. And I even picked up a good local student, Danny, and with whom we worked on friction models. But around this time, I was getting I was building this multisensory environment called the Haven, which was going to provide an ultimate multisensory display with an acoustic chamber and things like that. But I also felt at this point that I need to get back to this question that I had in grad school about how the body really works. And one of the things about being a tenured prof who's at that point a full prof is that I could afford to take risks. So I felt that this is a good time for me to get back to those questions and try to understand how the body works. And I was always bothered by this type of a textbook picture in neuroscience textbooks, which says that, okay, this is how you would, for example, play a key. Your brain generates some signals at the top, and it goes down, handed down through the spinal cord and activates a muscle, and it does is what you want to do. So, but the problem is that the real data were suggesting otherwise. So one thing is that, of course, we know that we don't always move in arbitrary ways. There are some stereotypical ways in which human motion is coordinated. So one question was, are these synergies in the brain, or could they be because of some mechanical complexity? So if you look inside your hand, you'll see that the tendons aren't just driving each joint individually, but they are coupled in some very complicated ways. And when you start looking at this, you realize, this is some very seriously sophisticated hardware that is being ignored by our models. The eye, by the way, from Helmholtz on down, has been treated as a kind of the hello world of sensorimotor systems because the eye seems very simple. It just has 3 degrees of freedom in rotation, 6 muscles organized in pairs, looking like as if 2 muscles control 1 joint degree of freedom, etc. But even this simple system turns out to be quite complicated. And fairly recently, people have discovered that there are all these tendinous mechanisms that are holding things in place. So the question is why? Why is it doing this? What is it telling us? So I think it told me 2 things. One is that we need these realistic computational models to understand what the brain actually does, and that biomechanics may not just be a complication, it's really part of the solution. It co-evolved with the brain. So I started looking into these questions with my students while keeping one foot firmly in graphics. So we try to look at these basic science questions, but try to publish the work in graphics. So Paul's PhD work was looking at the fact that when we interact with objects, it isn't just the motion, but also how the forces are generated passively due to the compliance of the joints or the muscles. And so Paul was able to measure both together at the same time. We call it interaction capture. And once you measure the compliance in the hands, then you can then transfer it to other motions easily. The other question was, you saw that these muscles are all in close contact. There are complicated tendon networks. How do we represent all of these complications? How do we deal with all the constraints and the contact between the two with large deformations? If you'd use the standard Lagrangian discretization of all of these muscles, you have to solve a lot of complicated contact problems and collision detection problems. So we had an insight at that time that Eulerian discretizations, which were typically used in fluids, would be actually great for these type of highly constrained systems. And this was done by Dave Levine, who's, I guess, now the general chair of this conference, and Shin Sueda, working together on different aspects of this. So, for example, we could model two objects like these penguins. We could simulate the soft tissue deformation by using an Eulerian discretization, which we later generalized to these Eulerian-on-Lagrangian discretizations that would allow you to deal with these contact problems very simply. And then we could use this for things like active muscles. So you could actually activate muscles by changing their rest shape, and that would drive the animation. And this was work done by E.A. Fan, initially with Dave, and then continued on afterwards. The other thing that we could do is, even to model these thin tendon-like structures, we could model them very efficiently with these Eulerian methods. For example, this famous painting of Rembrandt's is actually a lesson in functional anatomy, not just the descriptive anatomy. What Dr. Tulp is showing is that if a particular muscle called the FTS, or the superficial muscle, is activated, it doesn't just bend the fingers in a normal way, but it bends at the proximal joint like this. And this has all kinds of consequences. So Shin initially, and then Prashant implemented these type of simulators which can use to simulate the actual tendinous structures in the hand. We used a similar method with the Chi Wei to model the orbital mechanics of the eye. I don't have time to go into the complexity of this, but this kind of funny visualization that you see on the right is depicting that even the muscles have multiple compartments, and the compartments behave differently, and then we are able to capture some of the kind of conditions like superior oblique palsy by modeling the mechanics of the orbit better. We also looked at, again, taking things from neuroscience such as visuomotor coordination, trying to make advances there by saying, how do we actually do things like intercept a visual target when you have just a few hundred milliseconds to quickly both estimate its trajectory and generate a motor program to do it. And it turns out when we implement that theory, the catching behavior also looks more realistic. And so you can see that the eyes and the hands are all coordinated in a perfectly natural way, but it's based on the neuroscience. So fast forwarding a little bit to the present time, I was also then struck by the question of how do you model real human tissues? So it's not enough to just do some passive excitation, watch people jump up and down and look at their tissues, because you don't compress the tissues enough, so you won't be able to pick up some of those types of modes. So you need to actually touch humans to measure their soft tissue properties, like how soft is their cheek, etc. So fortunately, as you know, we have solved a similar problem before with the ACME. So one thought is you could put people in ACME, but there are challenges for measuring real humans. So first of all, it has to be done in vivo, and people don't stand still, and you have to cover large areas, and you have to do this fast, so because the participants will otherwise get bored and go home. And finally, the tissue is complex. So I started another quite large project, which is still ongoing, with funding also from industry and from NSERC I2I program to measure real human bodies. So this is a little video that UBC Public Affairs put together that I'll just play out. So we're also looking at, for example, how impacts accelerate the soft tissues of the body. This is work of Calvin Close. We measure, instead of the ACME robot probe, we built a handheld probe which we track in real time with a motion capture system to estimate tissue properties. And one of the things that you could do with these type of realistic human body models is that you can predict how clothing fits in a better way. So I just want to step back here a little bit and just talk about some recent adventures that I've been having in startup land, and to come back to a couple of things. Over the course of my career, I've developed lots of technologies. A couple of things I didn't talk about was this interface called the Tango, which you can use as a passive haptic device, texture sensor. Here is a haptic interface for grasping objects, which can learn to the realistic grasp shapes and things of that sort. But these never got out of my lab. I had this naive view that if we build technology, people will pick it up and it will have an impact. Maybe one of the most I would say annoying examples is this paper with Kankan, which we did at Rutgers. Was we figured out that we could just measure foot pressures and simultaneously measure full body motion. And we can learn to correlate the two and generate the full body animation from just foot pressures. So this was in 2003, and about 4 years later, we didn't do anything about it, by the way. We just published the paper in SCA, I think. And 4 years later, Nintendo developed this Wii Fit, which essentially does something very similar. So, so I figured that we really want to, if you want to get these things out, we can't just expect someone else to do it. So I started a startup with a couple of my former students, Darcy and Ye, with advice from Rod Barman, who you remember was my engineer on the Platonic Beast project. He had later gone on to start a very successful computer vision company called Point Grey Research that had just been sold for a lot of money. So he had some time to help us out, figure out how things go. Initially, we thought we would target the visual effects market, and it was kind of interesting. We got some uptake from, for example, it got used in a movie, but it wasn't a good fit for us because our core interest was in building realistic models of real things and not just of fantastic beasts. So we did a pivot, and so we are now looking at the apparel market. It's still too much in process for me to draw any lessons and share that with you. Maybe I'll do that at a future date. So just to wrap up my talk, I think I'm almost out of time. So a few take-home messages. So which maybe in the interest of time, maybe I'll just go very quickly through it. So first of all, I think you need to listen to the problem. And this is, I think I need to have a longer chat to explain what exactly this means, but don't be over-constrained too early. Keep an open mind. If the problem tells you something, for example, that it is nearly impossible to touch an object without making a sound, maybe you should be studying sounds. Respect reality. And this means that, all the knowledge we have is layered. We build layers of abstractions upon abstractions. And at some point, we confuse the abstractions for what the reality is. So it's very useful to go back from time to time, look at the real system, do some measurements. I make at least many of my students who work on human bodies to take a gross anatomy course in the medical school, because by dissecting real humans, you understand really the complexity that we are missing. And finally, don't be afraid to take risks, because first of all, this is something you should do only after you've done the first two. Now, don't take some random risks, but at some point you have to take action based on all the things you've learned. So I like to think of doing research as like skydiving, in the sense that you want to prepare, you want to make sure that your parachute is okay, but you can't open the parachute in the plane. You have to jump out. You need the wind of reality against you to open the parachute, and hopefully it works. So I want to finish. I just want to quickly thank funding agencies, all my students from many years ago. I try to show some pictures. Obviously, I missed many. This is the type of things we do as a lab, have picnics and stuff like that. 10 years ago. This is from 6 months ago. And this is my lab today. I see them on Zoom. Calvin is just finished his postdoc and will be starting a faculty position in UBC in biomedical engineering in next month. Thank you very much. I'm happy to take questions.
Thank you very much, Dinesh. That was a really wonderful talk. It's really amazing to see, it's so gracious of you to include photos of all the people that you've worked with. And, it's remarkable what an impact you must have been just a great role model. So many of these students went on to become faculty who have then graduated great students. So really commend you on that. So we have time for questions for Dinesh. So if you're joining us for this talk, the Q&A button, you can click on to type a question, or you can raise your hand in the participants tab below, and then I'll call on you and I can unmute you. Let me get over to that now. Yeah, so maybe to get things going, I'm really intrigued by your work on material property capture and probing the world around the robot to see how a shape moves. Can you talk a little bit about how this could be deployed in an environment that's less like a lab setup and more out in the world, where you don't know yet if you're dealing with a rubber egg or a chicken egg or a hollow egg that might be super fragile? Like, how do you, yeah, how would you approach that kind of problem?
This is a very good question. So there is a lot you can do with just, of course, with video, and I think that's been happening quite a bit, especially with recent advances in in machine learning and things like that. The big challenge is when you have to look at either compression properties or sound properties where you have to excite the system. You can't just look at it passively. And there it is a bit of a problem. I actually had a student, Alistair, who has worked on something exactly like that to see if we can deploy some of these measurement systems on a mobile device. It should be coming out relatively soon. Yeah, so this is one thing, but it is a big challenge actually. But I think my initial goal is to see if we can capture the material, and then we can approximate it by saying, how can you get that quickly in a home set?
Excellent. We have a question from Brian. I think, Brian, you should be able to unmute yourself.
Okay. Dinesh, you mentioned when you were looking at the way muscles fired, the signals going to the muscle to fire it. For a piano player, on a grand piano, the key actually fires. There's a little sort of area where there's a kind of bump in the mechanism, so it can fire and reset in milliseconds. But is that commensurate with the nerve firing that? Because when a pianist does a trill, it's incredibly fast. I just wondered if there's something is happening above the level of the at a faster level than the muscle is able to fire.
That's an excellent question, actually, because this is one of the things that you realize when you look at biomechanics of muscles and the nervous system. A lot of your assumptions, or our assumptions, are by looking at how electronics and other devices work. And then you realize that actually the nervous system is very slow. The fastest nerve fibers propagate signals at the speed of sound. Okay, so, and it takes you about 70 milliseconds for the signal to reach from your fingers to the first kind of hop in your spinal cord and back. So you can't close the loop and work more than something like 10 hertz. So then the question is, how is the brain managing to do this? And I think the answer is related to the type of things that Paul did in his PhD work. The brain does this by kind of pre-programming the passive properties of the muscles. So the muscles you should think of not as a motor that is passively or slavishly following orders, but it is a kind of a local device that you can program to make it behave like any material that you want. Not any material, but you can make it stiffer, you can make it softer. And I think this is the way people can do these very fast physical motions, because you are programming the dynamics of your hand and your fingers to do the right thing. and at that point, your brain is not involved directly, except in a supervisory role. I hope that does it answer your question?
Yes, indeed. Yes, thank you.
So we have a question from the Slack here. So Mohammed Reza asks, what was your pose estimation or key point, I don't know how that's pronounced, method, and how much was the accuracy?
So I think this is probably referring to the human motion the human tissue measurement. So the pose estimation, I'm not sure I remember exactly the numbers, but what we do is we track the probe with a Vicon system. So I think it's on the order of like a sub-millimeter accuracy at that point at the tip. In terms of the body pose, we have markers just around the region where we are making contact, and that also has a comparable accuracy.
Let's thank Dinesh and congratulate him again on this wonderful award. Thank you so much, Dinesh.
Great. Thank you very much. It's been my pleasure.